Welcome to this lecture on animal behavior. Today, we are diving into the fascinating world of sign stimuli. Have you ever wondered how animals seem to know exactly what to do in critical situations without ever being taught? We will explore the hidden triggers in nature that hardwire survival skills directly into an animal's brain. Let us get started. To begin, imagine you are driving and see a red traffic light. You hit the brakes instantly without analyzing the shape of the light pole or the surrounding buildings. Your brain filters out the noise and reacts solely to that red light. In the animal kingdom, creatures possess similar built-in traffic lights. These are highly specific natural triggers that command an animal to act automatically, even if they have never encountered the situation before. These secret passwords of nature are what we call sign stimuli. Now that we understand the basic idea, let us look at the formal science. In ethology, which is the study of animal behavior, a sign stimulus is defined as a very specific, distinct feature of a complex environment that elicits an innate, stereotyped response. When an animal detects this specific cue, it triggers what biologists call a fixed action pattern. This is a sequence of unlearned, hardwired actions that run to completion once started. The animal does not need to think. The simple trigger directly activates the complex behavior. To see how this works in reality, we look at the pioneering work of Nobel Prize-winning ethologist Nico Tinbergen. He discovered that animals often ignore the big picture and focus on isolated cues, like a specific color or shape. For instance, a male European robin fiercely defends its territory. Tinbergen found that the robin will aggressively attack a simple tuft of red feathers placed in its territory. Amazingly, it will completely ignore a perfect, life-sized replica of a robin if it lacks that red breast. The red color alone is the sign stimulus. You might wonder why nature relies on such simple cues instead of processing the whole picture. The answer is survival. In the wild, a split-second delay can mean the difference between life and death. By using sign stimuli, an animal's nervous system saves immense amounts of processing power, allowing for instantaneous reactions to predators or prey. If a baby bird had to learn its mother's exact face before begging for food, it might starve. Furthermore, understanding these triggers is vital for conservationists, who must recreate them to encourage natural breeding in endangered species. Now that we understand the biology, let us translate this into mathematics. We can model how strongly an animal reacts using a simple threshold equation. R equals K times the quantity S minus T. Here, R is the response intensity, like the number of pecks a bird makes. S is the strength of the sign stimulus, such as color contrast. T is the innate threshold, which is the minimum stimulus needed to trigger the behavior at all. Finally, K is a sensitivity constant that changes based on how hungry or aggressive the animal is. If the stimulus S increases, the response R grows proportionally. Let us apply this formula to a real scenario. A newly hatched herring gull chick pecks at a red spot on its parent's beak to get food. We are given an innate threshold T of 2 units, a natural stimulus S of 7 units, and a hunger sensitivity K of 3. We want to find the response intensity R. First, we substitute our values into the equation. We subtract the threshold 2 from the stimulus 7, giving us an effective stimulus strength of 5. This means the stimulus is strong enough to trigger the behavior. Multiplying this by the sensitivity constant, 3, we get a final answer of 15 pecks per minute. The calculation we just performed reveals a fascinating vulnerability in animal behavior. Because the response increases proportionally as the stimulus gets stronger, what happens if we present an artificially massive stimulus? This leads us to the concept of a supernormal stimulus. A supernormal stimulus is an exaggerated, artificial trigger that actually produces a stronger behavioral response than the natural object it mimics. The animal's brain is hardwired to follow the math. Bigger stimulus equals bigger response, even if the object is completely fake. Let us see how this changes our previous calculation. Researchers test this by presenting the chick with a bright red stick instead of a real beak. The chick's internal biology remains exactly the same, so the threshold T is still 2 and sensitivity K is still 3. However, the fake stick has a massive contrast value, making S equal to 12. We substitute these into our formula. Subtracting the threshold 2 from the new stimulus, 12, gives an effective strength of 10. Multiplying this by 3, we arrive at a final response of 30 pecks per minute. The physical reaction has doubled simply because the visual cue was artificially enlarged. Let us pause and think about what that result of 30 pecks per minute truly means. The chick is reacting twice as aggressively to a piece of painted wood than it does to its actual living parent. This mathematically proves that the animal is blindly following its innate programming. It is not looking at the object and thinking, "Is this my mother?" It is simply detecting the color contrast and executing the fixed action pattern. This vulnerability shows how easily nature's code can be hacked by supernormal stimuli, turning a life-saving shortcut into a rigid trap. Let us bring all of this together visually. On the screen, you can see the natural parent's beak on the left, providing a moderate stimulus that triggers a normal feeding response. On the right is the supernormal stimulus, the exaggerated red stick that hijacks the chick's attention. Below them is a graph plotting our mathematical model. The horizontal axis is the stimulus intensity, and the vertical axis is the response rate. Notice how the response stays at 0 until the stimulus crosses the threshold T. From there, the line slopes upwards steadily. The jump from S equals 7 to S equals 12 clearly shows the proportional spike in the animal's behavior. We have covered a lot of ground today, so let us summarize the key takeaways. First, sign stimuli are highly specific biological shortcuts that trigger innate, unlearned behaviors known as fixed action patterns. Second, these mechanisms evolved because they provide incredible speed and efficiency, saving animals from fatal hesitation in the wild. Third, we can accurately predict these behaviors using the mathematical threshold model we explored. Finally, because the system is so rigidly hardwired, it can be easily exploited by exaggerated, supernormal stimuli. You now have a solid understanding of how evolution programs the animal mind. Great job!